what is a virtual network by one or more IP ranges. When I say IP here, we always think IPv4, but as we'll see later on, it could be IPv6 as well. It always has to be IPv4, but it may also add some IPv6. Now, typically, we're going to use RFC 1918 for that. So those are IP addresses that are set aside that we can use on our internal networks. You probably have it at home. You'll maybe see your IP address is 10 dot or 192.168 dot. And the point of these IP addresses, they won't route over the internet. If they get to anything that's on the internet, it's just going to drop those packets. So every company could use the same addresses because they won't route or clash when they actually get to the internet. Now, this address space is then broken up into subnets, just like we would a regular network. Have a physical network, then maybe we have floors of a building, parts of a data center. They'll get a portion of that IP space. Now in Azure, a certain number of IP addresses from every subnet are reserved. The regular ones just for IP, the all zeros and all ones, well, they're always set aside for. The network address and the broadcast address. Then Azure will also take an additional 3, which we'll see when we draw this out. And subnets are regional. They span availability zones. So while in some clouds, hey, a subnet has to be bound to a particular availability zone, which remember is that particular group of data centers with independent power calling networking, that's not the case in Azure. I can have services really all over the place and it doesn't impact anything. So if we think about these constructs for a second, so remember we said, okay, well, I have a subscription. Remember, I can create many things within a subscription. So we have this boundary that is the subscription. Now within the subscription, I can create things in many, many different regions. But here I'll pick a specific region. Maybe it's South Central US, it could be East US too, doesn't matter. But within a particular region I'm using, within those two boundaries, I can create a virtual network. So I can think about, okay, I've created I'm going to call it VNet1. Now the whole point is that virtual network we're defining by at least one IPv4 CIDR range. So a CIDR is a way to write down a particular network and how many bits make up that network. So I might think about, well, I have to have one IPv4 CIDR range. For example, I might say, hey, say EG 192.168/16. So that's an RFC 1918 range. Now another RFC 19 range is 172.16. And remember, this /16 is the number of bits that make up the network mask. So it's 32 bits in IPv4 range. Send the dot something, hey, I can use whatever I want within there. There's also a 172.16/12, so it's only using half. So this could actually go up to sort of, beyond the 16. And then there's 10/8. So I might, hey, 10.0.1.0 could be a particular subnet that I use within here. But this is this RFC 1918 ranges. You don't have to use these. If I own some great big range on the internet that I've purchased as a company that's actually internet routable, I could absolutely bring a portion of that to the virtual network. But just because it's routable on the internet, these will not be routable. They'll still be private IP addresses used only within the virtual network. So it would really be a waste of the IP space to bother assigning them right here unless there was some really, really good reason. So we have at least one, but I can have additional. So I can change the CIDR ranges for a virtual network. I can add, I can even remove, providing it's empty. I've managed to empty everything out of using that particular block of the addresses. Now within that virtual network, I create subnets. Now let's say in my example, just for we think about the IP ranges I might use, let's say what I actually used in my virtual network was, this is 10.0/16. So I'm using a portion of that 10 space. I'm using, hey, the 10.0 that I could then break up into subnets. So for this first subnet, so this is my subnet 1, I have to use a portion of that space. So maybe I'm going to make subnet 1, well, it has to start with 10.0 because that's the virtual network's address space. So the /16 is saying this is the network, then I'll use a portion of that. So maybe I'll do 10.0.0/24. So now everything within this subnet would be those. I might create a second subnet. So I can have another subnet, subnet 2. Well, its IP range has to come from this range. It can't be the same. I can't overlap. Maybe this is 10.0.1.0/24. As you can see, it's just moving along, and I'm using whole 8 bits per subnet just to make it simple for me. Now, when I create these subnets, remember, the whole point is we lose a set of IP addresses. So whatever this range is, so say that was a /24, I always lose 5 IP addresses. Now the all zeros, so for example, if this was a /24, so I'm making an assumption just so it looks easy when I write this down, but the .0, well, that's the network address. The .1 is always used for the gateway. So Azure is providing the gateway service. Even if resources are in different subnets, they can automatically just talk to each other because Azure is providing that gateway for us. The .2 and the .3 are reserved for DNS purposes, and then the all ones that make up the host address, so for example, .255 in my example, well, that's used for broadcast. So those are reserved. So I always lose 5 IPs from any virtual network. So no matter what that size is, so if I create the /29, there'd only be 3 usable IP addresses. So /29 would give me 8 addresses. But I lose 5, so it would give me 3 usable. So a /29 therefore becomes the smallest possible in Azure. Because anything less than that, there won't be enough even to give it the reserved IP addresses it wants. So that's always going to be the way for those. So think about these constructs. And remember, as I mentioned already, we have those availability zones in most regions, AZ2, AZ3, AZ1. Subnets span them. There's no alignment of a subnet to a particular availability zone. They do not care. They can just cross over those. And then I would create resources. So, okay, great. I'll create a VM. And when I say I create a VM in the subnet, it's not really the VM. What really happens is that VM has a virtual NIC. And it's the NIC that connects and is bound to a particular subnet. in a particular virtual network. So now you would say that VM is in this subnet, but again, we know really it's not the VM. Its network interface card that's connected to the VM is connected to a particular subnet. So this is our virtual network. It's bound to a particular region, cannot span regions, cannot span subscriptions. And this is built on and used by nearly everything in Azure. Most things inhabit a particular virtual network. That's just the way these resources are constructed. Okay, so then we get a virtual machine network interface card. So I drew that on the picture, the idea of, hey, there's this NIC. The IP address from a virtual machine always comes from the Azure Fabric. This will be thought of within the guest operating system as DHCP. Now, I can reserve a particular IP address from the subnet the VM is connected to for a particular virtual machine. So if I was a domain controller, a SQL server, I can absolutely configure it so it always gets the same IP, but the guest operating system, it thinks it's using DHCP. Now the exception to this would be, well, I have multiple NICs, so I can have multiple NICs connected to it, but then if I had multiple IP configurations, well then I'd have to do some configuration inside. Now you can have multiple NICs, but they have to be connected to the same virtual network. So they could be connected to different subnets, absolutely, but if I go back to the picture and we think about this, so this VM, remember the NIC is just connected into a subnet. It could absolutely have another NIC connected to this subnet, but it could not have a NIC connected to a subnet in a different virtual network. Every subnet it connects to has to be in the same virtual network. And if you think about the use of multiple network cards, that's useful in a physical world. In a physical world, there's pieces of wire attached that connect to physical hubs, that connect to physical other pieces of wire, copper, fiber, whatever it is, so it actually separates up my connectivity. This is all software-defined networking. The use of multiple NICs becomes a lot less useful in a software-defined networking world. It's better to use network security groups and rules to control traffic. I can use routing to control things. Now, there may absolutely be scenarios where I have rules assigned. So maybe this is a DMZ, this is some backend, this is some particular workload, and I want a network virtual appliance. To a virtual machine with special software, in which case, sure, I want it to have NICs so it can connect to the different subnets which all do different things. Maybe it's routing in between them. But the point is it's a lot less common to need multiple NICs than it is in the real world, because this is all software-defined networking that's actually achieving this. So now if I think about going back to this, many VM types also support accelerated networking. So what is accelerated networking? So if I think about the regular way this works, so I just said software-defined networking, and when I talk about a virtual machine, so the whole point of a virtual machine is there's some bare metal, so there's some bare metal hardware I could think about, and then we're running a hypervisor. So there's some hypervisor. In a Hyper-V world, the hypervisor is really concerned with CPU and memory. And then there's this parent partition. And the parent partition, because of the flexibility of requiring different types of driver, and I don't want those in the hypervisor directly, this parent partition runs and connects to other types of hardware. So if I think about the network interface card, the NIC, the physical NIC on this bare metal piece of hardware, well, it's actually the parent partition that is bound to that NIC. And it has something called a Hyper-V switch that enables all of the connectivity. So the Hyper-V switch actually connects to the NIC. And then when I create my virtual machine, and it has that virtual NIC, well, the NIC connects to the virtual switch. Great. The virtual switch is where we have all these virtual filtering platform components that do the various bits of routing and checking and all that magical great stuff. It adds a certain amount of latency. Well, what we can also do is there's technologies like SOIOV that exist in Hyper-V and in the hardware, where these network cards also expose things called virtual functions. So it might have multiple virtual functions on it, just go draw 3 of them, that really can expose themselves like they're actual physical adapters. So what accelerated networking does is instead of it going via the Hyper-V switch, it gets bound to a particular virtual function. Oh, use my color. So it goes this way. So this is when I turn on accelerated network. It bypasses the Hyper-V switch. It basically just reduces latency, it improves performance. Not every VM SKU supports it, but many of them do. So if I see the option there for accelerated networking, go ahead and turn it on. Inside the operating system and inside what's really happening is there's actually still a regular virtual NIC as well. They bind them together because there are certain times maybe it's being moved, something happens, and it has to break away from the virtual function, goes back via the virtualized, the synthetic NIC. But in other times it will then switch back as best it can. So if you see accelerated networking, turn it on. All it does is give you goodness. There's not a downside to it. If it's available, you really just want to leverage it. Okay, so many of them do support accelerated networking. I can have multiple IP configurations per NIC, as I was talking to. So if you think about an IP configuration, this is the idea of, hey, a certain IP address. It's always a private IP, i.e. from the range of that subnet, but maybe I also want a public IP. And if we jump over for a second if I was to just look at a NIC, so I'm just going to look at this demo NIC right here, we notice we have, so notice firstly, I guess the important thing here is the NIC is its own resource in Azure. It is an actual resource. It's an Azure Resource Manager resource. It is connected to a certain VM. It's bound to a particular virtual network and subnet. Then notice the one does not have accelerated networking, but I could change that and enable it. And then it has its private IP address. This one also has a public IP address. So it has to have a private IP. Optionally, I can also bind a public IP. And then I can see it's attached to a particular VM. It does not have IPv6. We'll come back to that. If I go to my IP configurations down here in my settings, on a single NIC, just like you could on a physical NIC, I can actually have more than one IP configuration, i.e. more than one IP address on a single NIC. So I could do add, and then I can say, well, do I want to add an IPv4 or an IPv6? I can only have one primary, which I already have, so it has to be secondary. And I can say, do I want this to be a dynamic or static allocation, and do I want a public IP with this IP configuration? So the whole point of this, remember, I can actually go and edit the existing one if I wanted to. Just look at this IP configuration. So the assignment by default is dynamic. It's going to take the next available usable IP address and use it for this NIC. But if this was something like a domain controller or a SQL box where I always want to have the same IP, I can change this to static, configure the IP address. Now remember, the virtual machine is still using DHCP. Hey, starts up, hey, I need an IP address, please. But the Azure Fabric, which acts as that DHCP server, will always reply with that IP address. It's not going to vary each time. Whereas if I have this as dynamic, then, hey, depending on maybe what started before it, it may get a slightly different IP address. Normally we don't care. Even if something needs to talk to it, normally it will go to DNS, and DNS will say, oh, this is its current IP address, because it will get registered as part of that IP address allocation and other processes. But this is where I can control that if I wanted to. But I can absolutely give multiple IP configurations to a particular NIC. And if I do multiple IP configurations, well then I have to manually, inside the guest, do configuration for those, because obviously there's no way for DHCP to give out multiple IP configurations to a single NIC. It just doesn't work that way. So if I do want to do multiple IP configurations, realize, well, hey, I can, but then that's the one time that I am going to have to actually do something in the guest OS to leverage those additional configurations. So I can have that. I always have a private IP. I can optionally add a public IP. And we're going to talk more about public IPs and how they flow just in a few slides' time. The number of NICs does vary depending on the actual type of VM. So if we look at some of the limits, this talks about, well, how many IP addresses can I have? So notice private IP addresses per VM, there's a lot of them. So per interface, I can actually have 256 private IPs and 256 public IPs per NIC. So I could have a lot of different IPs per NIC if I wanted. Now these are really focused around IPv4. IPv6 today has some very different limitations from that. It's nowhere close to those numbers. In fact, I think it's one today. I think you can have one IPv6 today. But I'm sure over time that will change. So supported types of traffic that I can have being used on that virtual network. And it really boils down to, it's most things that sit on top of IP. So IP is a layer 3. So then if it sits on top of IP, it will probably work. Now, things like TCP and UDP, which are layer 4, they sit on IP, they work, they're tested. And by working, the important thing is they work with other components of the virtual network. So if I had network security groups and rules, those rules understand TCP and UDP. Load balancers, well, they have rules that can be defined in terms of TCP and UDP. May other layer 4 things work? Sure, but those components within Azure may not understand them, and so you won't be able to operate those with things like the load balancer or NSGs. Also ICMP. So ICMP we typically use for ping. Hey, I want to check if something's there, I send out an echo request to something, and then if it's there, it will send back that response to me, a reply. So that's how I can go and check something. So those things are supported within my virtual network. So if we go and look at our picture, when I think about the types of traffic I can use, I'm thinking about, well, at the layer 3, and by I say layer, this is OSI, the old Open Systems Interconnect, I think it stands for, and this is IP. At the layer 4, well, it's TCP and UDP. And then ICMP is also supported. Now, I'm drawing that kind of in the middle because there's sometimes debates about is ICMP layer 3 or layer 4. I mean, obviously it works with IP, but it kind of sits next to it. And so I'm drawing it in the middle so I can avoid that whole argument. But those are primarily what I'm going to think about using in my virtual network. Now, I cannot use multicast. Multicast is where I can target multiple IPs from a packet. I cannot use broadcast. I can't say, hey, everyone. I cannot use encapsulation, so IP and IP packets. I cannot use generic routing encapsulation, GRE. Azure is using this for its own software-defined networking. So there are limits on some of the functionalities that I can do within a virtual network. I can't ping the Azure gateway. If I try and ping the .1, it's not going to respond to me. Because again, this is software-defined networking. If I think about what is a ping is actually sending out to that end device, hey, ping request, please echo request this packet back to me. I'm sending you a packet, send it back to me. There is nothing at .1 to actually be able to send it back. So I can't ping the gateway. Also, tools like traceroute are not going to work with the gateway. Also, I can't use things like VLANs. There is no layer 2 here that I'm going to be able to leverage as part of this. I can't sniff in a promiscuous mode. So promiscuous mode network sniffer is, hey, I put a device on network and it looks at all of the packets that are going over the network wire. There is no network wire for the NIC. It's being sent packets targeted to its customer address on this software-defined network. I can't look at packets that are going over the wire to other people. They'll never get to my NIC. I can look at packets that are for me or from me locally in my VM, but that's all I can do. Now, Azure has some tracing and packet capture capabilities as part of Network Watcher, for example, but within the guest, I can't look at packets for other people. I can't deploy my own DHCP server. It's not going to work. Those packets will never get received. Azure grabs them and it replies so it can give out IP addresses. So there are definitely limitations to certain things that I might be able to do. What about IPv6? IPv6 has become very popular. And I have a whole separate video on IPv6. Actually talking about what is IPv6 and then how it relates to Azure. But the whole point is, I can absolutely enable IPv6 for a virtual network. So I drew this idea here that a VNet is one or more IPv4 CIDR ranges, but I can absolutely also optionally add on IPv6 CIDR ranges. And the whole point of IPv6 is it's much, much bigger. If a regular IPv4 is 32 bits, an IPv6 is 128 bits. And the idea really is, and I can't remember what the actual number is, but there's thousands or millions of IP addresses for every square foot on the planet. You're not going to run out. IPv4 basically ran out. We've done clever things with network address translation to make it keep working. But IPv6 is so big, we're not going to run out. So this was the idea that no matter how many wearables you have and how many microwaves or toasters have an IP address, IPv6 laughs and says, hey, I've still got plenty of space for that. So it's not going to be an issue. So the idea is that I can enable for a particular subnet an IPv6 address once the VNet. So then at a subnet level, I can say, hey, I want a portion of whatever IPv6 that I might want to use. Now, typically, you're going to use the idea of, well, there's different types. But there's things like, there's link local. So I can have something that I generate myself. But I can also have certain unique addresses that, like RFC 1918, won't actually route on the internet. So if you see FD, FD is basically starting off the address that it won't route on the internet. And I can use whatever I want within my own virtual network. So there are once again IP address ranges that are reserved that I can use internally. And if we went and looked at my network quickly, so if I jump back over here for a second, and what we can see if I go and scroll down, let's go and look at my VNet for a second. And I think it's my dev connect, and look at my address space. So it's on my address space, what I can see over here is I've got an IPv6 address space as well. So you can see it's an IPv6 range. Now notice it starts with FD. So FD is that local range of IP addresses, so it won't actually route on the internet. And it's a /56 because, well, it saves another set of bits that I can actually use as part of the subnet. So if this is the range I'm using here, and I'm using a portion of it, my actual subnet would always be a /64. So here, you see basically my subnet is 1, but that is my subnet. And notice available IPs, it's just saying more than 10,000. It's always a /64 for IPv6. Because the address space is so big, I don't ever have to worry about trying to make subnet some weird /27 or 20. We just make it a /64. It guarantees it's going to work with all different types of routers and devices, and there's such a big IP space, I don't worry about it. It guarantees future compatibility. So it's always going to be this /64 for the subnet. It won't let you do anything else. And there's just so many IP addresses. And now the VM inside it, if I was created, for example, in that infra, it would also get an IP address from that range. So if I was to think about for a second, well, let's just jump over really quickly. So if I go and look at my VM, let's go over here for a second. So if I get to my VM, come on, show the VM. Why is it not showing? Get there in a second, I promise. There we go, there's my VM. So if I do an IP config, notice my IP addresses. Well, I've got that IPv6 address, and it's from that FD. And notice it's the :1, which was my subnet, and its IP address is 4. So that's the sum of its, the 64 bits for the actual host address is 4. That's all it needs. It's the first usable IP. Again, I always lose 5, so the first 4 are taken, 0, 1, 2, 3. So it uses 4. You'll see it also has this FE80, which is a link local address that's auto-generated. It's like the old IP address we got if we used DHCP and a server couldn't be found. Was it 169 or something? That's the equivalent of there. But we can see that my VM running in Azure, therefore, has this IPv6. So I have my regular IPv6, I have my link. I always get a link local. I can't turn off the link local in IPv6. I'm always going to have it, but those are available for me. So I can absolutely add IPv6 as well if I'm ready to use it. Now, things like network security groups we're going to talk about, user-defined routes, load balancers, peerings all support IPv6. But it's always dual stack. I cannot do just IPv6. I have to have an IPv4. It's used for some of the management traffic. It's used for other things. I can add an IPv6 to my config. I cannot be IPv6 only. So think about today, it's always dual stack if I want IPv6. And dual stack means in the networking stack, it has an IPv4 and an IPv6 as part of that. VMs support IPv6. Virtual machine scale set supports IPv6. AKS has support for IPv6 in the KubeNet scenario, where it has its own IP address range for the container networking. It does not support IPv6 for CNI today. So the exact configuration is going to vary today based on exactly what is the workload you're doing. But peering works. If I create a public IP address, so let's jump back over to that for a second. So if I was to try and create a public IP, it'll actually give you a choice. It'll say, well, hey, do you want this to be IPv4, IPv6, or maybe you want it to be both? So I hit create, and it gives me that choice. So many, many things I can now use, if I want to, IPv6. Things like ExpressRoute, private peering, so connectivity from Azure to my on-premises network, it can use IPv6. That's available for me as well. I can enable it for existing resources. So I could go and add an IPv6. I could then add it to the subnet. Depending on the OS, maybe it'd have to restart, maybe not. It does depend on the exact operating system. And as I said, ExpressRoute can support it as well. And I already talked about the public IPs. External access. All these IP addresses I've been talking to so far have been within the virtual network. They're a private IP space. There is no special DMZ or internet-facing subnet in Azure. Some clouds have the concept of a subnet has to be marked as external facing, and is not the case in Azure. There is no subnet where everything just gets a public IP. By default, Azure provides an outbound SNAT, so a static network address translation based on ports, so port address translation, enabling resources to access the internet and receive responses. So before I go on to the next part, so what this means is, let's redraw our little virtual network for a second. So if I think about, okay, I have a virtual network, I have a VNet, and then within the VNet I have a certain subnet. Within that subnet, I have some resource. Could be many resources, whatever it is, but I've got a resource, could be VM, whatever, I've got a group of them. And then floating out in wherever is the internet. Dun, dun, dun. Other stuff. Things inside a virtual network, just by default, can talk to the internet and they'll get a stateful response back. It won't just let anything in, but it will let the response come back in. Now, this is going to work, so this is going to be allowed, so it's using SNAT. Now, this is that whole idea, remember, that the internet is just a whole set of networks that are connected and can route. They know how to get to something, or at least what's a hint for the next hop to go to be able to get to something. The internet is just a bunch of connected networks. Well, because they're connected, they have to be able to route, which means they have to be valid IP address ranges. But we already said our virtual network is probably not. It's this RFC 1918, it's non-routable. So what has to happen is I need something at the edge that is a valid public IP. And what SNAT does is, well, hey, I have this valid IP. You have a bunch of non-public valid IPs. When you, private IP address, make a request, I can specify a source port. And if you think about the port number, I think it's about 64,000 usable ports for any one IP address. So I'm going to map port 4000 to this particular request from VM1. Port 4001, I'm going to map to this request from VM2, and etc. So one IP address can handle a huge number of contiguous requests from different clients. So this SNAT is provided, well, in different ways. There's an implicit. So an implicit is just there's some public IP created that you don't really see or know about. If I just have a VM and I try and talk to the internet, it will do this implicit method. It will go and allocate a public IP and it will use it to provide this SNAT service when you go out to the internet and let the responses come back. Or I can do explicit. This is where I'm actually defining something. Now, one way is I actually have an instance level public IP. This is saying, hey, VM, in your IP configuration, you also have a public IP. Now, the guest OS still doesn't really know what that public IP is. It has nothing to do with it. It's the Azure Fabric. When a response comes into this public IP, it will just send it to the NIC of the virtual machine. The VM doesn't know it has that public IP. But in this case, if I have an instance level public IP, I'll use that to do my outbound internet. Another option is I'm using a standard load balancer. I'm saying standard. It would also work with basic. Basic is really on the way out, which is why I'm not emphasizing that. Actually, one of the nice things about basic is even if it was an internal load balancer, this external stuff would still work. If I have a standard load balancer and it's internal, it will actually break the ability for workloads behind it to talk to the internet. So if I have workloads behind a standard load balancer and it's internal, I have to also put it behind either a public standard load balancer, or I can use something called a NAT gateway. So this is a specific service designed to provide outbound. And for all of these, I give them a public IP or a public IP prefix. So a prefix is a set of continuous IP addresses. Maybe I need multiple addresses. I need them to be one after each other. So I can use a prefix. The benefit here of something like NAT gateway is it's designed purely to do NAT, outbound. I can define the IP addresses. It will dynamically use as many public IPs as it needed. As it fills up those 64,000 ports per IP, it will go and grab another one. Depending on the amount of workload coming in. The standard load balancer, outbound rules can also use an IP prefix, but I have to think about it more in advance and plan it out more in advance. So this is designed for that outbound type access. But hey, I can also do it with outbound rules with a standard load balancer. But realize the key thing is if I'm behind an internal standard load balancer, I don't do anything, those workloads won't be able to get to the internet. I have to do something else. Add a public standard load balancer that they're behind as well, or give it an instance level public IP. We almost never want to do this, by the way. Almost never do I want an instance level public IP. In fact, I'm going to draw my famous frowny face. Like, there's very few scenarios I ever want to do an instance level public IP. And we'll talk more about that later on. But that's just not a great thing to do. Really, I want to use one of these to control it. And of course, the benefit here, this implicit one, I have no idea what this public IP address is going to be. It's just something. Whereas with both the standard load balance and a NAT gateway, I'm defining the public IPs so that if there are things behind these services that try and access some other thing on the cloud, well, I know what IP the request is going to be coming from, so I could actually whitelist out that particular IP on that target service if I wanted to.